Imagine you are walking into a high-stakes AI and machine learning engineering coding interview.
Oh, yeah. The classic whiteboard scenario.
Exactly. The whiteboard is just staring back at you. Your marker is capped. And, you know how to code, but in this room, knowing how to write code simply isn't enough.
Right, because the interviewers sitting across from you, they don't just want to see if your code works.
No, they absolutely do not. They want to see if your system can actually scale for, like, massive AI data sets. Because here is the brutal truth, right? Without BigO notation, you just write code. But with BigO, you design systems.
That is honestly the perfect way to frame it. The stakes are entirely different when you move from, building a small side project to architecting data pipelines for millions of users. It's a fundamental shift in mindset. You're basically moving from a coder to an architect.
Exactly. And
Yeah.
to really test that mindset, let's start with an anchor problem. So I want you, the listener, to imagine you are in that interview room.
The pressure is on.
The pressure is definitely on. And you've come up with two possible solutions for processing a massive data set. One solution runs in a when, and the other runs in ON squared.
Okay, classic setup.
Right. So which is better for large N? I want you to pause and think about how you will solve this interview coding question.
Take a second, yeah.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
And our mission for this deep dive is to give you a really intuitive, foundational understanding of fundamental data structure and algorithm patterns. Specifically, focusing on BigO notation today.
Right.
We want you to be able to instantly recognize common patterns, to think purely in worst-case performance, and explain your code's complexity exactly like a highly hireable candidate during a really high-pressure, time-bound interview.
I love that. Highly hireable. So we're talking about passing the interview by writing scalable code. But before we even get to the whiteboard, we really have to define what BigO actually is.
Yeah, we have to clear that up.
And maybe more importantly, what it isn't. Because I know when I first started, I thought it was literally like a stopwatch.
Oh, totally.
Yeah, I thought we were measuring how many milliseconds a script took to run.
You're definitely not alone in that. I mean, it is the single most common misconception out there. BigO is absolutely not a measurement of exact time.
Right.
We don't measure it in seconds or milliseconds because, well, hardware changes. A script is going to run way faster on a brand new machine than on some, 10-year-old laptop.
Makes sense.
Instead, BigO is fundamentally a growth story. It measures how your solution's performance degrades as the size of your input, which we call N, grows.
Right. So if we have an input size of 10, say, our data set is just 10 images. Any code you write is going to feel incredibly fast.
Oh, blazing fast.
Yeah, it doesn't matter how horribly written the loop is. Your computer will process 10 items in a blink.
Precisely. But what happens when N equals 1 million? Or like a billion?
Which is pretty standard.
Exactly.
Yeah.
In machine learning, processing 1 million data points is standard. It's just a Tuesday. When you hit that kind of scale, the difference in algorithmic efficiency doesn't just increase, it absolutely explodes.
Wow.
What's fascinating here is that efficiency really only matters when scale increases. Like, a slow algorithm stays slow no matter what massive, multi-million-dollar AI supercomputer you throw at it.
Okay, let's unpack this.
Sure.
I want to push back on that a little bit.
Sure, go ahead.
We are talking about modern AI here. If I have an entire cluster of, say, H100 GPUs, surely I can just sort of brute force my way through a poorly optimized algorithm. Like, where is the actual breaking point where the hardware just gives up?
Okay. That is a very, very common trap candidates fall into. They just rely on compute power. But let's look at the actual math.
Okay, let's hear it.
Let's say you write an algorithm that is ON squared. If your data set is 1 million items, N squared means your system has to perform 1 trillion operations.
1 trillion. Okay.
Now, scale that to 1 billion data points, which is a pretty standard language model training set nowadays. 1 billion squared is 1 quintillion operations.
Oh, wow.
Yeah. Even an entire cluster of top-tier GPUs will completely choke on that. It would literally take years to process what a well-optimized ON algorithm could do in a few seconds.
Okay, that puts it in perspective. So relying on a supercomputer to run a poorly optimized ON squared algorithm is like, well, it's like putting a lawnmower engine inside a Ferrari.
Yes, exactly.
The car looks fast, the paint job is incredible, but the engine still completely limits how fast you can actually drive.
That's a great analogy. You simply cannot out-hardware bad math. The growth rate is the engine, And as engineers, we have to look at the code we're writing on that whiteboard and instantly understand the growth rate of that specific engine.
So we know the lawnmower engine is bad, obviously. But how do we accidentally build one? Like, let's look at the actual coding patterns that trap people.
Good idea.
How does this theoretical idea of growth map to the architecture we're building in Python?
Let's build it from the ground up. Think about the most basic operation you can do.
Mm-hmm.
A single loop over your data.
Just a standard for I in range.
Exactly. You are iterating through your entire data set one time. Whatever happens inside that loop is going to execute exactly n times.
Right.
If n is 10, it runs 10 times. If n is 1,000,000, it runs 1,000,000 times. The relationship is perfectly linear. So we call this ON.
That part is pretty intuitive. It's just a straight line. But what happens when we nest things? Like, I write a loop to go through my data set, and for every single item in that data set, I run a second, fully internal loop over the entire data set again.
Well, now you've fundamentally changed the growth story. You have just created the lawnmower engine.
Oh.
Because for every single iteration of the outer loop, the inner loop has to run its entire course of n times.
Right, so we are multiplying, but let's make sure we understand exactly why we multiply instead of add.
Think of it like household chores. Imagine you have n dishes to wash and n shirts to fold.
Okay.
If you wash all the dishes and then completely separately you fold all the shirts, your total amount of work is just dishes plus shirts. That is sequential.
So that's adding.
Exactly. But a nested loop is very different. A nested loop means for every single dish you wash, you must stop and fold in shirts.
Oh, man. That sounds like a nightmare.
It is. You wash one dish, you fold 1,000,000 shirts. You wash the second dish, you fold 1,000,000 shirts. The workload multiplies exponentially. You have n times n. That gives us a time complexity of ON squared.
Okay, yeah, the chore analogy makes the danger of nested loops terrifyingly clear. ON squared is a massive red flag for large AI datasets.
Yes, it is. But here is where candidates often fall into a critical trap during those whiteboard interviews. They understand nested loops multiply, but they get entirely confused by parallel loops.
The sequential chores, right. Okay, paint that picture for me. What is the parallel trap on a whiteboard?
Imagine you write a script with two completely separate blocks of operations. Top of the script, you loop through your entire massive data set once to, say, clean the text.
Got it.
Then, entirely outside of that loop, further down the script, you write a second loop going through the data set again to tokenize the text.
Okay, so wait, if I have two separate loops of n, isn't that mathematically twice as much work? Shouldn't the interviewer want me to say the complexity is O2n? Why do people say it's just ON?
That is the exact trap. You're falling for it. The logical rule is that parallel sequential loops ADD together. So time equals ON plus ON.
Right, which is O2n.
Mathematically, you are 100% correct. That is O2N. But in BigO notation, the final answer you give the interviewer is simply O-pen.
Wait, I can't just accept that. We're engineers, right? We care about precision. Why do we just delete the two?
I know it feels wrong at first.
If I have 1,000,000 data points, O2n means 2,000,000 operations. That's an extra 1,000,000 steps. How does 1,000,000 steps just disappear?
It disappears because of what we call the rule of dominance. Remember, BigO is not a stopwatch. It is a growth story focused entirely on the shape of the curve as we scale toward infinity. I want you to visualize a graph.
Okay, I have a graph in my head.
If you zoom way, way out on that graph to where the x-axis represents billions or trillions of data points.
It's like really zooming out.
Yeah, massive scale. The line for n and the line for 2n look basically identical. They're both just gentle, straight slopes. The constant multiplier of 2 doesn't change the fundamental shape of the line. But if you look at the line for n squared on that same graph, it isn't a gentle slope. It is a vertical wall shooting straight up in the stratosphere.
I see. When we are dealing with numbers so massive that they crash supercomputers, a flat scaling factor of 2 is essentially just a rounding error compared to an exponential explosion.
Exactly. We only care about the biggest engine driving the growth. So let's apply this. What if you have a nested loop, followed by a single sequential loop, followed by a single operation that pings a server?
Okay.
Mathematically, the architecture is ON squared plus n plus 1.
If my algorithm is ON squared plus n plus 1,
Okay.
well, I drop the constant, so the 1 is gone,
Yep.
and I drop the lower order term, so the single n is gone. The final answer I give the interviewer is just ON squared.
Precisely. For incredibly large values of n, that extra rel plus n is microscopic. It simply does not matter. The n squared component is going to be responsible for like 99.9% of the processing time.
That makes the math so much cleaner to communicate. And, it proves to the interviewer that you actually understand how systems behave at scale rather than just doing elementary arithmetic on the whiteboard.
Right. It shows, what actually impacts a system in production.
Mm-hmm.
And this brings us to another really critical aspect of the engineering mindset, worst case thinking.
Worst case.
Yeah, BigO is fundamentally about the worst case scenario.
Which makes sense, but why the absolute obsession with the worst case? What if my algorithm is usually really fast?
Give me an example.
Take searching an unsorted array for a specific user ID. The best case is that the ID I am looking for happens to be the very first element. I find it on the first try, boom, one step, 01.
That is true, but engineers do not design AI data pipelines based on luck.
Fair enough.
The worst case scenario is that the user ID you're looking for is the absolute last element in the massive array, or maybe it isn't in the array at all.
Oh, right.
Your code would have to check every single element before it knows for sure. That makes the fundamental architecture an ON operation. If we connect this to the bigger picture.
Yeah, why is that worst case obsession so vital for AI and machine learning specifically? I mean, what happens if we just assume an average speed?
Well, because in AI, you are building autonomous data pipelines. They run at 3 a.m. without any human supervision.
Okay, yeah.
If your system is designed assuming an average case speed, it'll be allocated a specific amount of server time and memory. When it inevitably encounters a worst-case, edge-case dataset in production, say a massive influx of malformed data, the algorithm slows to a crawl.
And then what?
The server times out, the entire pipeline breaks, downstream models fail to train, and literally millions of dollars can be lost. You guarantee stability by mathematically planning for the worst.
That is a terrifying but very real scenario. Okay, so we've established the baseline. ON is checking everything once, which is safe, but scales linearly.
Right.
And ON squared is our nested loop lawnmower engine, which will eventually crash our pipeline. But I know that in high-level coding interviews, checking every item once isn't always good enough.
Yeah, they'll always push you.
They'll look at an ON solution and ask, can you do better? How do we possibly get faster than checking every single item once?
To do that, we have to entirely change our approach. We have to develop what we call logarithmic intuition. We are talking about O log n.
O log n. See, that is the notation that always sounds incredibly intimidating to candidates.
It sounds like complex calculus, I know, but the mechanism is beautifully simple. Let's use an analogy. Imagine an old-school physical phone book.
Remember those?
Barely. But imagine it has 1 million pages in it. Now, if you are searching for a specific name, say Smith, using an ON approach, what are your exact mechanics?
I am starting at page 1 and flipping through every single page one by one, reading every name until I find Smith.
Exactly. And in the worst-case scenario, Smith is on the very last page. It takes you 1 million steps. That is OM1.
Makes sense.
But there's a catch here. A phone book has a special property. It is sorted alphabetically.
Right. And because it's sorted, I would never actually read it page by page. I would just open the book to the middle.
Exactly. You open the book exactly to the middle. Let's say you land on the letter M. What happens next?
Well, I know Smith comes after M alphabetically, so I know for a fact that the name is not in the first half of the book. Oh, here's where it gets really interesting. Because the data is presorted, I can literally take the entire first half of the phone book, rip it out, and throw it in the trash. I just destroyed half the SERP space in a single step.
Yes. You just eliminated 500,000 pages of data without having to read a single one of them. This only works because the data was sorted first.
That's amazing.
Then you take the half you kept, open it to the middle again, and repeat the process. You throw away another 250,000 pages.
So instead of 1 million steps, if I just keep cutting the remaining pages in half, how many steps does it actually take to find one specific name out of 1 million pages?
Try doing the math in your head. Half of 1 million, half of that. It only takes about 20 steps.
That is staggering. 1 million steps down to 20 steps. That isn't just an optimization. That is a completely different paradigm of computing.
That is the power of logarithmic growth. It barely grows at all, even as the dataset becomes massive. So the strict rule to remember for your interview is this. If the algorithm's mechanism divides the problem size by half at each step, you should immediately think O log n.
Let's lock that in. I want you, the listener, to hold that phone book scenario in your mind. If your code successfully divides the search space by 2 at each step of the operation, what is the complexity?
Just give it a second.
The answer is O log n. And remember the critical prerequisite the expert just pointed out. You can only rip the book in half if the data is already sorted. If the phone book was in random order, you'd have no choice but to check every page.
Spot on. Now, before we put all of this together into a final whiteboard test, there is a massive blind spot we really need to address. So far, we have been talking entirely about time complexity, how fast the algorithm executes its operations.
Right, the speed.
But top-tier AI engineering interviews will heavily grill you on space complexity as well.
Space complexity. So if time complexity is how many operations, space complexity is how much memory or RAM does this algorithm consume while it runs.
Precisely. And in machine learning, memory is often your biggest bottleneck.
Let's expand on this because I feel like this gets glossed over in standard coding tutorials. Why is space complexity so uniquely critical for AI and ML candidates?
Because of how AI models are trained. We train models on GPUs, and GPUs have a very strictly limited amount of memory, what we call VRAM.
Okay.
Let's say you have an algorithm that processes a matrix of 1,000,000 parameters. In terms of time, it runs incredibly fast. But let's say your code is written in a way that it creates a duplicate copy of that matrix for every single operation.
Oh no. That means the space complexity is O(n) squared.
Exactly. Even if the time complexity is O(n), if your space complexity is O(n) squared, the moment you feed that into a neural network, your batch size will instantly exceed the GPU's memory.
Boom.
Yeah, the program will crash with an out-of-memory or O error. It doesn't matter how fast the math was going to be because the system literally exploded from memory bloat.
So generating an array of n elements in Python takes O(n) time to run loop. But because you are storing n discrete elements in a variable, it also permanently occupies O(n) space in your RAM.
Yes. And as an engineer, you have to balance the two. It is a fundamental trade-off.
Right.
Sometimes making an algorithm faster in time means it requires caching data, which takes up more space and memory. Sometimes saving memory means the algorithm has to recalculate things on the fly, making it slower in time. The interviewer wants to see you weigh that trade-off out loud.
Okay, we have covered a massive amount of conceptual ground here. We've talked about multiplication for nested loops, addition for parallel chores, the rule of dominance dropping those constants, the necessity of worst-case thinking for pipeline stability, the phone book ripping power of O log n, and the GPU crashing reality of space complexity.
It's a lot, but it's essential.
It really is. So I think it is time to bring all of these rules into a single practical interview stress test.
Let's do it. Let's see how all these pieces fit together. This is exactly how it will look on the whiteboard.
All right, picture the architecture in your mind. You are looking at a script with 3 distinct blocks of code running top to bottom.
Visualizing it.
First block, you have a single for loop iterating over your entire massive data set to clean out null values.
Okay.
Second block, directly below that, completely separate, you have a loop that simply pings a diagnostic server exactly 1,000 times.
Right.
Third block, at the bottom of the script, you have a nested loop. An outer loop goes through the data set, and an inner loop goes through the data set again to compare every single data point against every other data point.
A classic setup.
So we have the cleaning block, the pinging block, and the comparison block. I want you, the listener, to hold that script in your mind for a second. What is the total time complexity of this entire function?
Let's break down the solution exactly how you should process it in the hot seat.
Okay, walk us through it.
First, we look at the top block. A single loop over the dataset. That is our linear baseline. It gives us O(n).
Simple enough.
Next, the middle block. A loop running exactly 1,000 times to ping a server. Now, some candidates might panic and say, oh, 1,000. But remember our rule about dominance and constants. Constants do not matter.
Because it's a flat number.
Right, because the number 1,000 never changes, regardless of how big the actual input data set gets. It takes constant time. So that block is simply O(n).
Okay, and the last block.
Finally, the bottom block. We see nested loops depending on the data set. The rule is nested loops multiply. So n times n gives us our lawnmower engine, O(n) squared.
So mathematically, adding our sequential steps together, our total equation is O(n) plus O(1) plus O(n) squared.
Correct. But we are not done. We must apply the rule of dominance. The dominant term always entirely dictates the growth curve.
So we look for the biggest engine.
Exactly. Between a flat line of 1, a gentle slope of n, and the vertical wall of n squared, the biggest engine by far is n squared. So the final answer for the entire script is simply O(n) squared.
Okay, so you have done the math in your head, you have correctly identified O(n) squared, but knowing the right answer is only half the battle in an interview. How you communicate this to the hiring manager is what actually gets you the job.
Oh, absolutely. This is where Think Aloud training comes in.
What's it look like?
This cannot be emphasized enough. If you just stare quietly at the whiteboard for 30 seconds, turn to the interviewer and confidently declare, this script is ON squared. You might be technically right, but that is a highly unhirable answer
Why is it unhirable if it's correct?
because it doesn't show your reasoning. For all they know, you just guessed.
Ah. So what does the hireable answer actually sound like?
A highly hireable candidate will narrate their architectural logic. They will point to the board and say something like, looking at this script, the first block scales linearly, and the second runs in constant time. However, I see a nested loop at the bottom, where the inner loop runs n times for every single iteration of the outer loop.
Oh, I see.
And then they'd finish with, because of this multiplication, the operations will grow quadratically as our dataset scales. The lower order terms will be dwarfed, so by the rule of dominance, the overall time complexity is ON squared.
That is beautiful. It is all about explaining the WHY, not just the what. You aren't just reciting rules. You are proving that you understand the underlying mechanics of the code, how the hardware will process it, and how it behaves at scale.
Exactly. You are demonstrating beyond a shadow of a doubt that you think like an AI architect, not just a junior coder memorizing Python syntax.
This has been incredibly revealing. Let's do a quick wrap-up checklist of the mental models we've built today.
Good idea.
If you are heading into an interview tomorrow, here are the red flags and mistakes you absolutely must avoid. First, never just say an algorithm is fast or slow. Always speak in the precise language of big O, like ON or O log N.
Yes.
Second, never fail to consider the worst-case scenario. Do not design pipelines based on luck or they will break in production.
So true.
Third, do not forget to drop those constants. A flat multiplier is a rounding error at the scale of infinity. Fourth, do not confuse parallel loops with nested loops. Sequential chores add, nested chores multiply.
And finally, do not forget space complexity. A fast algorithm that crashes the GPU's memory is a failed algorithm.
If you can internalize those core rules and narrate your logic aloud, you are going to be head and shoulders above the vast majority of candidates walking into that room.
And mastering this specific deep dive makes all the upcoming material incredibly obvious.
Oh yeah, the next ones are great.
In future sessions, we are going to look at actual code optimization. We will take an algorithm that runs horribly slow at ON cubed, and we'll apply these very concepts to optimize it down to ON squared, and eventually down to a blazingly fast ON.
But you cannot optimize what you cannot measure, which is why today's foundation was so vital.
It truly is the bedrock of system design. But, as we wrap up, this raises an important question. This is something to think about as you continue studying AI architecture.
Lay it on us.
Well, we have established that BigO forces us to always design mathematically for the absolute worst-case scenario. We have to prevent the pipeline from breaking. But what happens in modern AI when a model's average case is lightning fast, but its purely theoretical worst case only happens 1 in a billion times?
Ooh.
Right. Do we still sacrifice everyday speed and efficiency just to optimize for an anomaly that we might never actually see?
That is a phenomenal question to chew on. Is the worst case always the only case that matters, or is there room for calculated risk? It brings us right back to that interview room.
Yeah.
You aren't just writing code on a whiteboard. You are making complex, real-world decisions about how systems operate in the wild. You are designing the future. Keep thinking like an engineer. Until next time.